So, welcome back to our projective geometry class. We're still in the slot where we care about axioms, and this time we want to draw a few first simple formal consequences out of our axioms. So, let me once more recall the axioms. I wrote them down now in mathematical shorthand. So the first axiom reads, for all points P and Q taken from our set P with P is not the same as Q, so the points should be distant. There exists exactly one, and I note this exactly one by this little dot over the extension qualifier. There exists exactly one L taken from the set L such that it is at the same time incident to P and at the same time incident to Q. Similarly, the second axiom, for any points L and M taken from, for any lines L and M taken from the set of lines with P, L is not the same as, here's a little mistake, M, there exists exactly one point P such that it is incident to both of them, and the third one, there are 4 points, no 3 of which are collinear. So now we want to make conclusions from that. And the first one is a little trivial, but important to keep in mind. And it's more reformulation than actually a lemma. So I call it lemma 2.1. Just one remark, whenever I write down theorems that are also in my book Perspectives of Projective Geometry, I refer to the lemmas and theorem numbers in the book. So now we're talking about lemma 2.1. And one way to state this is that the incidence graph is square free. So you remember the incidence graph was a graph where we said that the points are represented by nodes in the graph and the lines are represented by also nodes in the graph. We have a bipartite graph, and incidence is expressed by having an edge between those two. And something like that, what you see here, can not happen in an incidence graph, and the reason for that, it would violate both axiom A1 and A2, because it would violate the uniqueness property here. So if you have 2 points, say P and Q, there should be only one line incident to them, but here you see there are 2 lines. So this cannot happen. And similarly, if you have 2 lines, then there should be only 1 point incident to both of them. Another way to state this is if you have all sorts of incidences, P is incident to L, P is incident to M, Q is incident to L, and Q is incident to M, then this implies that either P and Q are the same, or that L and M are the same. It's another way to think about it. A third way to think about it, it's also forbidden to have that in the incidence diagram. Whenever you have drawn 2 points, there cannot be 2 lines passing through both of them. We will need that in our investigations in a moment. So our next little lemma is a little bit less trivial, and it states the following: every line is incident to at least 3 points. So as a matter of fact, this must be something where axiom A3 comes into place, because we have seen if we omit A3, we get situations where there are lines that who are only incident to 2 points, or just to 1 point, or to no point at all. So here we really need axiom 3. And let's see what happens. So let this here be just one generic line, and we have axiom 3. And axiom 3 tells us there are 4 points somewhere in our projective plane. It could happen that 2 of the points, but at most 2 of those points, are on line L. So you should bear in mind that, say, these 2 points could be as well here on our line L, but no 3 of them, because axiom 3 says there are those 4 points, and these should be the 4 points from axiom 3, such that no 3 of them are collinear. So in particular, we can say that this point A here, that this point A is not incident with L. And well, what can we do? We can apply axiom 1 and say, well, there must be lines that join point A to the other 3 points. Again, keep in mind, say C and D could still lie on L. So these 3 lines here must be different from L, because they have the property that A lies on them, and L has the property that A lies not on them. So if they are distinct lines, there must be intersections of those lines, and these 3 intersections must be 3 different points, because assume that 2 of them were equal, then we would have such a forbidden situation where we have 2 points and 2 lines coincident to each of mutually. So these 3 points really must be 3 distinct points, and this proves our theorem. Every line, so our red line here was chosen generically, is incident to at least 3 points. It still may happen in that drawing that these 2 points are the same and these 2 points are the same, but it wouldn't change the fact that you have at least 3 points on your line. So we could transfer our richness structure somehow to a certain richness statement among lines. So next lemma makes use of that. For every point P, there is one line L not incident to P, another richness statement. So assume you have a point P, and you may have lines lying around, and say if you have a line L that is somewhere, you do not necessarily, if this L is somewhere and not incident to P, then you already are done here. So the only interesting case is that if all lines really pass through that point P. But now our last lemma comes into play and says, well, on each of those lines there have to be more points. There have to be 3 more points, but already 2 suffice for what we are doing now. And we see, you have 2 more points, and those 2 points by axiom 2 have to be connected by axiom 1, have to be connected by a line. And this line cannot be incident to L, otherwise we cannot be incident to P, because otherwise we would violate the small forbidden axiom. So this line here really is not incident to P. And so in that case, if we label this one L, we proved our theorem. So this was a simple one. Now let's get to the first thing that I really would call a theorem. If you have a projective plane with only finitely many points on it, then the number of points on each line is a constant. So if you have a finite projective plane, then it happens that each line has exactly the same number of points on it. Remember the Fano plane? There we saw that each line had exactly 3 points on it. This was a special case of that theorem here. So we are going to prove that by well, comparing the numbers of points on two different lines. So assume we have a line L and a line M, and what we now will prove that on the line M there are at least as many points as on the line M, as on the line L as a first step. So assume that on that line you have a certain number of points, and well, be careful. Our two lines are lines in a projective geometry, so they must meet in one point, and well, this one point must be, one of those points must be at this intersection. Then we saw that by our last lemma, there will be a line that is not incident to that point. So let me draw that line here. So here we have that line, and I have safely drawn this line through one of those points because, well, it must have an intersection with line L. And so one of the intersection points must be that point here. We know by lemma 2.1 that on that line there are at least 3 points, and I draw one of those points and the second of those points. One of those points I can draw safely at line M, and this cannot be the same as here because then we would get a forbidden substructure, because M and the red line must have one point in common. So, but then there must be one more point here, and by axiom 1, we can connect this point here to each of the other points on L. And now by axiom 2, each of that lines can be intersected with line M, and we get a number of points here. So each point here corresponds to a point here. So from each point here, we can construct one point on line M. You could even call that a projection here. So if you look at that, we project line L on M through this I point here. So you see perspectivities shine through at that point. So these points, the green points, all have to be different because otherwise we would get forbidden substructures in our incidence system. And so we see each point here generates a green point here, and this point here is on both lines. This implies that M has at least as many points as L. We can reverse this argument and in the same way can argue that L has at least as many points as M, and this means both have the same number of points. And so we can say these two statements together imply our statement up there. And so the number of points on a line in a finite projective plane is a constant. Just a brief reminder, no, not a reminder, another fact here. This number here is extremely important. And actually in literature very often not this number is really important, but 1 minus this number is important. And this 1 minus this number is called the order of a projective plane. So if we remember our Fano plane, the Fano plane was a plane of order 2. Okay, let's make the next statement. Actually, in the book, it's part of theorem 2.1 as well, so I call it 2.1 prime, and it states through every point there are n plus 1 lines as well. So we have seen if n is the order, so n should be again the order. We have seen if n is the order of a finite projective plane, then on any line there are n plus 1 points, and symmetrically through any point there are n plus 1 lines, and the proof is close to trivial. So take a point, take any line, take all the lines that go through that point, take any line not on that point, not through that point, and we just proved that we have altogether n plus 1 points here. So this means that we have altogether n plus 1 lines here. So this was really a little sidekick of the other theorem. But now we can take all that together and count the total number of points in a finite projective plane, and this is what we will do next. So just a little reminder, if you look at the Fano plane, you see that through each of the points there were exactly 3 lines. So, next theorem, a projective plane of order n has exactly n squared plus n plus 1 points and n squared plus n plus 1 lines, and the proof is a direct consequence of everything we did so far. So let's have a look. So we have a projective plane of order n, and we just have seen that through such a point we have altogether n plus 1 lines. On each of those lines here, we know we have n plus 1 points. One of those points is already played by our white point here. So here there are altogether n other points left. And this happens on each of those lines. So let me annotate it once more. So you have n plus 1 lines and n additional points, and you have this 1 point here. So all in all, you get n plus 1 times n plus 1 points, and well, if you multiply that out, you get exactly what we've written there, n squared plus n plus 1 points, and a completely symmetric statement holds for the line. Just reverse every time you set point in that proof, replace that by line, and every time you set line, replace it by point, and you get the count for the lines as well. I want to make a little side remark here. I want to write that as n squared plus n to the 1 plus n to the 0, and then you can imagine how that would continue, and this here is what will happen in higher dimensions. But we won't cover that here. So far for the moment. Next we will enter the realm of homogeneous coordinates.